Good morning to everyone. The slides I'm going to present to you are related to the research activity carried out by Mr. Paolo Lucchi during the year 2010. The PhD of Paolo Lucchi is organized in collaboration with the University of Bordeaux, where Professor Jean-Baptiste Bégueret is the co-tutor of Paolo Lucchi. The research activity is focused on the design of CMOS circuits able to work in the millimeter wave frequency range. So why these high frequencies? Up to now, all the wireless applications fall in the range of 1 to 10 frequency, gigahertz frequencies, but in this frequency range, the data rate is upper bounded by a value of around 100 megabits per second. If we want to move to higher data rate, we need to improve the frequencies. And in this case, if we use a frequency in the range of 60 gigahertz, we are able to achieve a data rate in the range of the gigabit per second. Even in this frequency range or higher, we find also other interesting applications, as in the case of automotive applications like radar or medical imaging. Here on the upper right corner, you can see a typical image obtained by the body scanner that you find in the airport. Why the 60 gigahertz? At 60 gigahertz, we have a very high absorption of energy. So in fact, if we select this frequency for the wireless applications, what we obtain is, in fact, a wireless network able to work on the short range. So we can use the same frequency in different rooms to connect different devices, as in this case, we are able to connect together multimedia devices inside the same rooms without using cables. For example, we are able to download a whole DVD in 2 seconds only. Why CMOS? In fact, today it's already possible to have a transceiver working at 60 gigahertz, but developed in compound semiconductor devices. This is already a commercial product that you can buy, and the data rate is in the range of 1.25 gigabit per second. But the main problem is the cost. The cost of this kind of industrial application is in the range of $20,000. It's very expensive. It's a very expensive device if you want to target a market, a mass market, as in the case of multimedia devices. So we can try to develop a similar devices, but using a lower cost technology. And the most suited technology for this kind of target is a CMOS. Here on your upper right corner, you can see that the main characteristics of the CMOS are high integration level, a low chip size, and what is most important, low cost. So you can get something small and cheap. But the main limitation of CMOS are the capability of working with high power and high frequencies. For this reason, the developing of millimeter wave CMOS circuit is a so challenging task and a so interesting research topic. The project, or better, the research activity carried out by Paolo is in the frame of a NanoCom project, a French project involving two French laboratories, the IMS laboratory in Bordeaux, where Paolo is working, and the LAS laboratory in Toulouse. The target of the research carried out in these two laboratories is the design of the PLL. Here we have a building block diagram of the PLL, and in particular for this PLL, the task carried out by Paolo was the design of the first frequency divider just after the VCO. These frequency dividers are very challenging to be designed because they have to work at very high frequencies, and in addition, as you know, they have to be designed in CMOS technology. The first divider was designed using an injection locking approach, and here on your left upper corner you see the schematic of the circuits, and here we have the diagram, the behavior of the Q quality factor versus the operational frequency. This is the most interesting picture to be discussed because here we can see the frequency range within the divider is able to work, and we can see that the circuit is able to work between 64 and around 71 gigahertz frequency. It is important to get some tunability, of the circuit. I mean, the circuit should be able, not exactly only at 60 gigahertz, but in a bandwidth around 60 gigahertz in order to be able to compensate for technological dispersions or temperature variations or bias variations. This is the layout of the designed chip. On the left, you can see the RF input. On the right, the RF output, and here the inductor, the integrated inductor, and so on. The chip has been already fabricated. The silicon is back from the foundry, and the experimental setup is in progress. The second frequency divider was designed using an injection locking ring oscillator. In this case, we can see that the main structure of the oscillator is a ring. I mean, is a cascade of several inverters. In this case, better than inverter, we are using a delay shell. The schematic of the delay stage is here on the left corner. And on the right side, you can see the layout of the design of the circuit. The most interesting remark that we can carry out is that in this case, we have no more inductor. And this leads to a very much more compact circuit. Again, here, more or less, we can see the frequency range where the circuit is able to work, and okay, the colors are not the best, but even in this case, the simulation shows that the circuit is able to work within a frequency range, able also to compensate for variations in technology, temperature, and bias. For the future, the next steps are the VCO design, which is already in progress just during this month, and the interface between the VCO and the frequency divider chain, because at so high frequency you cannot believe that you can simply connect your VCO to the frequency dividers. It's like impossible that this approach can work. They run, I mean, the tape out of the circuit to the foundry is scheduled at around the end of March of this year, so 1 month. And the final goal of the research activity is to get a fully integrated CMOS PLL. This is the main target, in fact, of this PhD activity. And the tape out for the PLL is planned at around the middle of June. So for this year, we expect to get the full PLL integrated on a die. These are the publications written by Paolo Lucchi, and thank you for your attention. If you have any questions, thank you.